In this lecture we'll answer on two questions. In the first question, we'll find out the area of this circle that is inside square ABCD. In the second question, we'll find out the value of the green area that is inside a quarter circle. Okay, so we'll start with the first question. In the drawing, we have square ABCD. Inside this square, we have a circle, and we also know that this angle CBT equals to 30 degrees, and line segment PD equals to 5 units. And our mission is to find out the area of this circle. Okay, so first of all, we'll define the center of this circle as O. We will join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of this circle that we define as R. We have the radius OP that is drawn to the point of tendency, therefore according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. This angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we'll join points O and Q together by a straight line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is also the radius of the circle that is equal to R. And we have the radius OQ that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. We also know that all the angles inside square ABCD are right angles, so this angle equals to 90 degrees, this angle equals to 90 degrees, this angle it is also equals to 90 degrees, and finally this angle it is equal to 90 degrees. Okay, so actually inside quadrangle AQPO we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees plus the size of the fourth angle. This angle in total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. So we have 3 angles that are in total 270 degrees, so the fourth angle must be also equal to 90 degrees, because 270 degrees plus 90 degrees, it is equal to 360 degrees, that is the sum of the angles in any quadrangle. So we found out that inside quadrangle AQPO we have 4 right angles. Therefore, quadrangle AQPO is a rectangle. I write it down. Quadrangle APQA is a rectangle because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AQ equals to side PO. AQ equals to PO. AQ equals to PO. But we have already found out that PO equals to R. It is the radius of the circle. And from this equation, AQ equals to PO equals to R, we will derive that AQ is also equals to R. EQ equals to R. So here we found out that AQ equals to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we'll get that AP equals to OQ. AP equals to OQ. But OQ equals to R, according to what we already found out, it is the radius of the circle. And from this equation, AP equals to OQ equals to R, we derive that AP is also equals to R. AP equals to R. Here, AP equals to R. So we actually found out that quadrilateral AQPO is a square and not a rectangle because of the fact that all of its sides are equal to each other, they are equal to R. Okay, we also know that all the sides of square ABCD are equal to each other. That is to say, side AD equals to side AB. AD equals to AB. Okay. AD equals to AB. What is the value of AD? AD equals to R plus 5. And what is the value of AB? The value of side AB, the length of side AB is R plus QB. So we found out that R plus 5 equals to R plus QB. Here we subtract R from this equation and we get that 5 equals to BQ. So we found out that BQ equals to 5. Here, QB or BQ equals to 5. Okay. In the next step, I'll present to you rule number 2 and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So here we have the common external point, point P. From the common external point, point P, we have tangent PA and tangent PB. And according to this rule number 2, PA equals to PB. So we actually can implement rule number 2 in our drawing. So in our drawing, we will focus on the common external point, point B. From the common external point, point B, we have two tangents to this circle. We have tangent BQ And we also have tangent BS. And according to rule number 2, they are equal to each other. Again, BQ equals to BS according to rule number 2. But we have already found out that BQ equals to 5 units, so we can write here BQ equals to 5. And for this equation, 5 equals to BQ equals to BS. We will derive that BS is also equals to 5. BS equals to 5. So here BS equals to 5 units. In the next step, we will join points Q and S together by a straight line. And here we have triangle QSB. In triangle QSB, those two sides are both equal to 5, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front the equal sides must be equal to each other. So if this angle is alpha, then this angle must be also equal to alpha because of the fact that those two angles that are located in front of equal sides must be equal to each other. So those two angles, they are both equal to alpha. What is the size of this angle? Angle QBS. Angle QBS equals to 90 degrees minus 30 degrees. Again, it is equal to 90 degrees minus 30 degrees. 90 degrees minus 30 degrees, it is 60 degrees. So this angle equals to 60 degrees. So we'll focus on triangle SQB. In this triangle SQB, this angle equals to 60 degrees. Therefore, the rest, the sum of the other two angles must be equal to 180 degrees minus 60 degrees. 180 degrees minus 60 degrees is 120 degrees. That is to say, alpha plus alpha must be equal to 120 degrees. Alpha plus alpha equals to 120 degrees. In triangle QSB, so alpha plus alpha is 2 alpha, so 2 alpha equals to 120 degrees. Here we divide this equation by 2 and we will get that alpha equals to 120 degrees over 2 is 60 degrees. Alpha equals to 60 degrees. So here angle alpha equals to 60 degrees, and here also angle alpha equals to 60 degrees. So inside triangle BSQ, this triangle, we have all the angles inside triangle BSQ are equal to 60 degrees. Therefore, triangle BSQ is an equilateral triangle. Triangle BSQ is an equilateral triangle. Why? Because all of its angles are equal to 60 degrees. Equilateral triangle. And we know that all the sides of an equilateral triangle are equal to each other. So here side BS equals to 5 units, side BQ equals to 5 units, therefore the third side, side AQ, must be also equal to 5 units. Okay, so SQ equals to 5 units. And in the next step, we'll join points O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of the circle that is equal to R. In the next step, I will copy quadrilateral OSBQ in a new page, and we will analyze quadrilateral OSBQ. Here we have the radius OS that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle, it is also equal to 90 degrees. So I'll copy quadrilateral OSBQ in a new page, and we'll analyze triangle quadrilateral OSBQ. Okay. Here angle OSB, this angle equals to 90 degrees according to rule number 1. This angle it is also equals to 90 degrees according to rule number 1, of course. So this is quadrilateral QBOS that I copied from the original drawing. Those two angles are both equal to 90 degrees according to rule number 1. We have already found out that this angle equals to 60 degrees, and we know that the sum of the angles in this quadrilateral must be equal to 360 degrees. Therefore, 360 degrees minus the sum of those three angles must be equal to the size of the fourth angle, the missing angle. So here the missing angle QOS must be equal to 360 degrees minus 90 degrees minus 90 degrees minus 60 degrees. That is to say, it is equal to 360 degrees minus 90 degrees minus 90 degrees is minus 180 degrees, and minus 180 degrees minus 60 degrees is minus 240 degrees. And 360 degrees minus 240 degrees, it is equal to 120 degrees. So we found out that the missing angle QOS, it is equal to 120 degrees in its size. So this angle equals to 120 degrees. So you can write here the missing angle QOS equals to 120 degrees. So in the next step, I will present to you the law of cosines, and we will implement the law of cosines in the green triangle, triangle QOS. Okay, so what is the law of cosines? The law of cosines is true in any triangle. So we have here a triangle ABC that could be any triangle. This is triangle ABC. And we know that the length of side AB is equal to A units, the length of side AC equals to B units, and the side BC equals to C units in its length, and the angle between side AB and side AC is theta. Then, according to the law of cosines, we will get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Okay. Repeat again. In triangle ABC, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Okay. Now we will implement the law of cosines in the green triangle, triangle QOS. So I will copy triangle QOS in the new page and we will implement the law of cosines in this triangle, triangle QOS. Well, actually, this is the triangle QOS that I copied from the original drawing. So, in this triangle QOS, according to the law of cosines, we get that 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. Okay, repeat again, 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. 5 squared is 25, that is equal to R squared plus R squared is 2R squared minus 2R times R is minus 2R squared times cosine 120 degrees. Cosine 120 degrees equals to minus 1/2. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. And we have minus times minus is plus. So in conclusion, we found out that 25 equals to 2R squared plus R squared is 3R squared. We divide this equation by 3. And we get that R squared equals to 25 over 3. And the area of any circle is equal to pi R squared. So the area of our circle will be equal to pi R squared. So it is pi and R squared. We already found out that R squared equals to 25 over 3, therefore we substitute R squared in this formula by 25 over 3. So we found out that the area that we are looking for, the area of the circle, is equal to either 25 pi over 3 square units, or in terms of numbers, it is equal to 50.265 square units. Okay, and that is the answer to the question. The area of the circle equals to either the area of this circle equals to either 25 over 3 pi square units, or in terms of numbers, it is equal to 50.265 square units. Okay. We finished with the first question. In the next step, I will present to you the second question, and we will solve the second question in 3 different methods. So, in the drawing, we have a quarter circle. Inside this quarter circle, we have a small circle. We know that line segment CD equals to 8 units, and we also know that angle ACD equals to 90 degrees, and our mission is to find out the green area, or the value of the green area. Okay, we'll start with the first method, and we'll define the center of this circle as J. We'll define the point of tendency of tangent CD with this circle as E. We define the point of tendency of tangent OB with this circle as F. We join points E and J together by a straight line. Point J is the center of the circle, point E is the point of the circle itself, therefore EJ is the radius of the circle that we define as R. Likewise, we join point J and F together by a straight line. So here, point J is the center of the circle, point F is the point of the circle itself, therefore JF is also the radius of the small circle that is equal to R according to our definition. And we have the radius GJE is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we have the radius GF that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees, and this angle will also equal to 90 degrees. We know that AOB is a quarter circle, therefore in any quarter circle, this point O is the center of the quarter circle, and this angle AOB, it is always equals to 90 degrees. And we also know that because of the fact that this is a quarter circle, AO must be equal to the radius of the quarter circle that we will define as capital R. Okay, AO is the radius of the quarter circle that is equal to capital R according to our definition. Okay, and so the radius AO as a radius, it is absolutely a straight line. So AO is a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have at this side of AO at point C? We have this angle is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Okay, so the missing angle, so the sum of those two angles is equal to 180 degrees, therefore the missing angle must be equal to 90 degrees. In order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees, this angle must be equal to 90 degrees. Okay, so in the next step, from point J, we draw perpendicular on CO. Again, from point J, that is the center of the small circle, we draw perpendicular on CO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point J in CO as T. Okay, so here inside quadrilateral TJOF we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. Therefore, the fourth angle must be also equal to 90 degrees. In order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be equal to 90 degrees. Likewise, in quadrilateral CETJ, we have 1, 2, 3 right angles. The sum of 3 right angles is 230 degrees. Therefore, the fourth angle must be also equal to 90 degrees. So I found out that angle EJF, this angle EJF, is equal to 90 degrees plus 90 degrees, that is 180 degrees. So angle EJF equals to 180 degrees. And therefore, angle EJF is a straight line. Angle EJF is a straight line. So if angle EJF is a straight line, then line segment EJF is a straight line, and if line segment EJF is a straight line, it means that EF is also a straight line. Here EF is a straight line. And if EF is a straight line, then quadrilateral CEOF is a rectangle. So I write it down. Quadrilateral CEOF is a rectangle. Why? Because it has 4 right angles. Okay, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to EF. In rectangle CEOF, CO must be equal to EF. But we have already found out that EF equals to R plus R, that is 2R. So here we can write down that EF equals to 2R. And from this equation, CO equals to EF equals to 2R, we will derive that CO is also equals to 2R. CO equals to 2R. Here, CO equals to 2R. Okay. In the next step, we join points O and D together by a straight line. Point O is the center of the quarter circle. Point D is the point of the quarter circle itself. This is exactly the definition of a radius. That is to say, OD is the radius of the quarter circle that is equal to capital R according to our definition. So in the next step, we will implement the Pythagoras theorem on the right green triangle, triangle COD. Okay, so in the right green triangle, triangle COD, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay. So the hypotenuse is OD, therefore the square of the hypotenuse is OD square. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to CO square plus CD square. I repeat again, the right triangle COD, according to the Pythagoras theorem, we get that OD square equals to CO square plus CD square. OD equals to capital R, it is the radius of the quarter circle, therefore OD square is capital R square. That is equal to CO square. We have already found out that CO equals to 2R, therefore CO square is 2R square, that is 4R square, plus CD square. CD is 8, so CD square is 8 square, that is 64. So in conclusion, we found out that according to equation number 1, capital R square equals to 4R square plus 64. We subtract 4R square for this equation number 1, and we get that according to equation number 1, capital R square minus 4R square equals to 64. So according to equation number 1, we found out that capital R square minus 4R square equals to 64. And what is actually the area of the green shape? For the drawing, it is very easy to see that the area of the green shape is equal to the area of the quarter circle minus the area of the small circle. Repeat again, the area of the green shape, it is equal to the area of the quarter circle minus the area of the small circle. That is to say, the area of the quarter circle it is equal to the area of the circle over 4. That is to say, it is equal to pi times capital R square over 4 minus the area of the small circle, that is equal to pi R square. So the area of the green shape equals to pi times capital R square over 4 minus pi R square. Here we take pi over 4 as a common factor out of those two expressions. And here, so pi over 4 is a common factor. What is left from pi times capital R square over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R square. And what is left from pi minus pi R square after we took from it pi over 4 as a common factor? What is left is actually minus 4R square. Why? Because minus 4R square times pi over 4 equals to exactly to minus pi R square. So here we found out that the area of the green shape equals to pi over 4 times capital R square minus 4R square. But here, this expression capital R square minus 4R square, it is equal to 64. Okay, according to equation number 1, it is equal to 64. That is to say, we can substitute capital R square minus 4R square by 64. And so we do it and we get that this expression in total equals to pi over 4 times 64. So 64 over 4 is 16. So in total, this expression equals to 16 pi. So in conclusion, we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 265 square units. Okay, so we finished with the first method. In the next step, I will present to you how to find out the area of the green shape according to the second method. In the second method, we will use in all the things that we have already found out in the first method. We have already found out that CO equals to 2R. We have already found out that this angle equals to 90 degrees. Here, this is the radius of the small circle, and this is also the radius of the small circle. We will complete. Here we already found out that AO is the radius of the quarter circle that is equal to capital R, and here this angle equals to 90 degrees. Okay. In the next step, we'll complete the quarter circle to a circle. So we completed the quarter circle to a circle. We'll extend the radius AO by a straight line until it intersects with the circle. We define the intersection point with the extended radius AO, and the circle is point T. We'll extend the straight line DC by a straight line until it intersects with the circle, and we will define the intersection point or the touching point of the extended DC and the circle as point M. We'll join points O and M together by a straight line. Point O is the center of the big circle. Point M is the point on the big circle itself. Therefore, OM is the radius of the big circle that is equal to capital R. Likewise, we join points O and D together by a straight line. Point O is the center of the circle. Point D is the point on the circle itself. Therefore, OD is the radius of the big circle that is equal to capital R. So here we extended the straight line DC by straight line. When you extend the straight line by straight line, the result must be a straight line. So therefore, DM must be a straight line. If we focus on the lower side of the straight line, DM at point C. Here the sum of the angles must be equal to 180 degrees according to rule number 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the lower side of MD at point C? We have this angle that is equal to 90 degrees. Therefore, the missing angle must be equal also to 90 degrees in order to complete the sum of the angles in the lower side of MD at point C to 180 degrees. This angle must be also equal to 90 degrees. So we created here two right triangles, triangle MCO and triangle CDM is also a right triangle. In the next step, we'll prove that those two right triangles can go into each other. Okay, so we'll prove that the right triangle, the right green triangle, triangle CDO, can go to the right triangle, triangle MCO. Okay. So why those two right triangles can go into each other? First of all, CO is a common side that belongs to both triangles, so CO equals to CO is a common side that belongs to both triangles. In addition, we have the radius MO. MO equals to OD, they are both the radii of the big circle, therefore they are equal to each other. So here, MO equals to OD, they are both equal to capital R, therefore they are equal to each other. So by proving that the hypotenuse and one perpendicular of those two right triangles can go into, we prove that those two right triangles can go into each other. I'll explain why. Because if you have, for example, two right triangles, you have a right triangle, triangle ABC. This is the right triangle, triangle ABC. And we have another right triangle, triangle DEF. So in those two right triangles, the hypotenuse of both those two right triangles are equal to each other. This is to say, both the hypotenuses are equal to 5. And we have side AB equals to side DE, they are both equal to 4. So if we have the hypotenuse and one perpendicular that can go in, as in this drawing, then the third side must be also congruent. Why? Because according to the Pythagoras theorem, the third side BC must be equal to the square root of 5 squared minus 4 squared. 5 squared is 25 minus 4 squared, that is 16. 25 minus 16 is 9, and the square root of 9 is 3. Here also EF will be equal to the square root of 5 squared minus 4 squared. That is also equals to 3. So found out that when we have two right triangles that are congruent to each other by their hypotenuses and one perpendicular, then the third side must also congruent. Here the third side BC equals to the third side EF, they are both equal to 3 units. Therefore, we actually proved that the right triangle, triangle COD, congruent to the right triangle, triangle COM, according to side rule. Why? Because when proved that the hypotenuse and one perpendicular congruent, the first side must also congruent. Therefore, those two right angles congruent to each other according to side rule. And from the fact that those two right angles congruent to each other, we will derive that CD equals to MC. CD equals to MC. And CD equals to MC according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the corresponding sides must be also equal to each other. That is to say, CD equals to MC. But we have already found out that it is given us the equation that CD equals to 8 units. And from this equation, N equals to CD equals to MC, we will derive that MC is also equals to 8 units. Here, MC equals to 8 units. MC equals to 8 units. Here, point O is the center of the big circle, point T is the point of the big circle itself, therefore OT is the radius of the big circle that is equal to capital R. What is the value of AC? Here, AC, from the drawing, it is very easy to see that AC equals to AO minus CO. Again, AO minus CO equals to AC. AC equals to AO minus CO. That is to say, AC equals to AO, that is capital R, it is the radius of the big circle, minus CO, that is 2R. So in conclusion, we found out that AC equals to capital R minus 2R. In the next step, we will implement, I present to you rule number 11, and we will implement rule number 11 in our drawing. So according to rule number 11, if we have this circle, inside this circle we have chord AB that intersects with chord CD at point O. So if this is the data that has been given to us, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule number 11 in our drawing, because I can implement rule number 11 in our drawing, because in our drawing we have chord AT that intersects with chord MD at point C. Again, chord AT intersects with chord AD at point C. I'll write it down. In our drawing we have chord AT that intersects with chord MD, before the MD, at point C. The intersection point is at point C. I'll repeat again. In our drawing, we have chord AT that intersects with chord MD at point C. Therefore, according to rule number 11, we will get that MC times CD, MC times CD equals to AC times CT. AC times CT. I'll repeat again. According to rule number 11, in our drawing, you get that MC times CD equals to AC times CT. MC is 8, CD is 8, so MC times CD is 8 times 8, that is 64. That is equal to AC. AC is capital R minus 2R times CT. What is the value of CT? CT equals to 2R plus capital R. Okay. So, in conclusion, we found out that according to rule number 11, 64 equals to capital R minus 2R times capital R plus 2R. This expression, capital R minus 2R times capital R plus 2R, according to the algebraic identity that A plus B times A minus B equals to A squared plus B squared, A squared minus B squared, of course. According to this algebraic identity, we get that in our specific expression, A equals to capital R and B equals to 2R. Therefore, here A squared minus B squared will be equal to capital R squared minus 2R squared. Okay, so we found out that 64 equals to capital R squared minus 2R squared. That is to say, 64 equals to capital R squared minus 2R squared. 2R squared is 4R squared. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. Okay? And what is actually the area of the green shape? The area of the green shape, it is actually equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R squared over 4, and the area of the small circle equals to pi R squared. Here we took pi over 4 as a common factor of those two expressions, and we have already found out that inside the brackets we will have here capital R squared minus 4R squared, but here capital R squared minus 4R squared, it is equal to 64. So we substitute capital R squared minus 4R squared by 64, and we get that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. Okay, so we finished with the second method. In the next step I will present to you how to find out the area of the green shape according to the third method. Okay. So in the third method, we do the things that we found in the first method. We have already found out that OC equals to 2R, AO equals to capital R, and AC equals to capital R minus 2R. This is the radius of the small circle, and this is also the radius of the small circle. In the next step, we'll complete the quarter circle to a semicircle. We'll extend the radius AO by a straight line until it intersects with the semicircle and define the touching point of the extended radius AO and the semicircle is T. Here point O is the center of the semicircle, point T is the point of the semicircle itself, therefore T is the radius of the semicircle that is equal to capital R. We extended the radius AO by a straight line, therefore the result that is AT, when you extend the straight line by a straight line, the result must be a straight line. So the result AT is a straight line, and the AT is a straight line that is equal to 2R, 2 times capital R. So you can see the straight line AT is a chord inside the semicircle that passes for the center of the semicircle. Any chord that passes for the center of the semicircle must be the diameter of the semicircle. So AT is equal to 2R, 2 times capital R. It is the diameter of the semicircle. Okay. And here we will join points T and D together by a straight line. We will join points A and D together by a straight line. So we created here peripheral angle ADT that rests on AT, that is the diameter of the circle, the diameter of the semicircle. And we actually have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of a circle or semicircle must be equal to 90 degrees. So here we have peripheral angle A and B that rests on AB, that is the diameter of the circle, therefore peripheral angle A and B equals to 90 degrees according to this rule number 5. And here we can implement rule number 5 in our drawing, because in our drawing we have peripheral angle ADT that rests on AT, that is the diameter of the semicircle, therefore peripheral angle ADT must be equal to 90 degrees. Okay, we define angle ATD as alpha, we define angle TAD as beta. We'll focus on triangle, the right triangle, triangle ADT. On the right triangle, triangle ADT, this angle equals to 90 degrees. Therefore, the sum of the two other angles must be equal to 90 degrees. That is to say, alpha plus beta must be equal to 90 degrees. Okay, alpha plus beta must be equal to 90 degrees. Why? Because 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Alpha plus beta equals to 90 degrees. Here we subtract beta from this equation and we get that alpha equals to 90 degrees minus beta. Then we subtract alpha from this equation and we get that beta equals to 90 degrees minus alpha. We will focus on the right triangle, triangle CDT. Here, actually this angle equals to 90 degrees according to the first method, rule number 3. So we'll focus on the right triangle, triangle CDT. In the right triangle, triangle CDT, this angle equals to alpha. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. So we found out that the missing angle here equals to 90 degrees minus alpha, but we have already found out that 90 degrees minus alpha equals to beta, so we can write here that this angle equals to beta. Likewise, we'll focus on the right triangle, triangle ACD. The right triangle, triangle ACD, this angle equals to beta. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus beta. But we already found out that 90 degrees minus beta equals to alpha. So we'll substitute 90 degrees minus beta here by alpha. In the next step, we'll prove that the right triangle, triangle ACD is similar to the right triangle, triangle CDT. So why those two right triangles are similar to each other? I'll write it down. We'll prove that the right triangle, triangle ACD is similar to the right triangle, triangle CDT. Okay. So why those two right triangles are similar to each other? So first of all, those two angles are both equal to alpha, therefore they are equal to each other. So angle ADC equals to this angle, that is actually angle CTD. They are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to beta, therefore they are equal to each other. So this angle, that is actually angle CAD, is equal to this angle, that is actually angle CDT. They are both equal to beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. That is to say, angle ACD equals to angle TCD. They are both equal to 90 degrees, therefore they are equal to each other. So we actually proved that the right triangle, triangle ACD is similar to the right triangle, triangle CDT according to angle similarity rule. And from the fact that those two right triangles are similar to each other, conclude that the following relationship exists between their sides. We conclude that AC in the right triangle ACD over CD in the right triangle CDT or CD equals to CD in the right triangle ACD over CT in the right triangle CDT. I repeat again, because of the fact that the two right triangles are similar to each other, we conclude that AC over CD equals to CD over CT. Okay. AC equals to capital R minus 2R, CD equals to 8, and CT equals to 2R plus capital R. So in conclusion, we found out that according to equation number 1, capital R minus 2R over 8 equals to 8 over capital R plus 2R. Here we cross multiply this equation number 1, and we get that according to equation number 1, 8 times 8 is 64 equals to capital R plus 2R times capital R minus 2R. So 64 equals to, according to what we have already found out, that capital R plus 2R times capital R minus 2R equals to capital R squared minus 4 times R squared. So according to equation number 1, we found out that 64 equals to capital R squared minus 4R squared. So what is the area of the green shape? Here, the area of this green shape, the area actually of this green shape, we are looking for the area of this green shape, of course. And the area of this green shape will be equal to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area of the green shape is equal to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R square over 4. We already found out that the area of the small circle equals to pi R square. We took pi over 4 as a common factor out of those two expressions. We have already found out that inside the brackets we will have here capital R square minus 4R square. And we know that capital R square minus R square equals to 64. This expression equals to 64. Therefore, we substitute this expression by 64, and we get that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16. So in total, this expression equals to 16 pi. Or in terms of numbers, it is equal to 50.265 square units. Okay. So we finished with the third method. In the next step, I'll summarize the lecture. We start with the first question, of course. In the drawing, we have a square ABCD. Inside square ABCD, we have a circle and we know that angle CBD equals to 30 degrees and line segment PD, this line segment equals to 5 units, and our mission is to find out the area of this circle. Okay, so first of all, we define the center of the circle as point O. We join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle, and we have the radius OP that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Then we join point O and Q together by straight line. Point O is the center of the circle, point Q is the point on the circle itself, therefore OQ is the radius of the circle, and is equal to R. Then according to rule number 1, we have the radius OQ that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. And we also know that ABCD is a square, therefore all the angles inside square ABCD are right angles. So those two angles and those two angles are right angles. So inside quadrilateral AQPO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, therefore the fourth angle must be equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So quadrilateral AQPO that has 4 right angles, it is a rectangle. And you know that the opposite sides of a rectangle are equal to each other. That is to say, AQ equals to PO. But here PO equals to R. It is the radius of the circle. So from this equation, AQ equals to PO equals to R, we will derive that AQ equals also to R. Here, AQ is also equals to R. Likewise, according to the same rule, that the opposite sides of a rectangle are equal to each other, we get that AP equals to QO. But QO equals to R, it is the radius of the circle. And from this equation, AB equals to QO equals to R, we derive that AP is also equals to R. Here, AP is also equals to R. So we found out that quadrilateral AQPO is not a rectangle but a square because all of its sides are equal to each other and they are equal to R. We know that in any square, all the sides are equal to each other. So in square ABCD, side AB must be equal to side AD. AB equals to AD in square ABCD. What is the value of AB? AB equals to R plus 5. What is the value of AD? AD equals to R plus QB. So here we found out that R plus 5 equals to R plus QB. We subtracted R from this equation, so R will get cancelled, and we found out that BQ equals to 5 units. Here BQ equals to 5 units. Then I presented to you rule number 2. According to rule number 2, and then according to rule number 2, we have the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From the common external point P, we have tangent PA and tangent PB. And according to this rule number 2, PA equals to PB. You can implement rule number 2 in our drawing, because in our drawing we have the common external point B. From the common external point B, we have tangent BQ and tangent BS. And according to rule number 2, BQ equals to BS. But we have already found out that BQ equals to 5. So here BQ equals to 5, and from this equation 5 equals to BQ equals to BS, we derive that BS is also equals to 5. Here BS equals to 5. Then you join points Q and S together by a straight line. Side in triangle QSB, side QB equals to side SB, they are both equal to 5 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle, they are equal angles. So those two angles that are located in front, the equal sides must be equal to each other. So if this angle is alpha, this angle must be also equal to alpha. What is the size of this angle? The size of this angle is 90 degrees minus 30 degrees, that is 60 degrees. Therefore, here 180 degrees minus 60 degrees must be equal to the sum of those two angles. That is to say, 180 degrees minus 60 degrees, it is 120 degrees. So 120 degrees equals to alpha plus alpha. So we found out that alpha plus alpha equals to 120 degrees in triangle PSB. In triangle QSB, alpha plus alpha is 2 alpha, so 2 alpha equals to 120 degrees. We divided this equation by 2 and found out that alpha equals to 120 degrees over 2, that is 60 degrees. So we found out that those two angles are equal to 60 degrees. Therefore, triangle QBS that has all angles that are equal to 60 degrees, it is an equilateral triangle. Triangle QBS is an equilateral triangle, and you know that all the sides in equilateral triangle are equal to each other. So QB equals to 5, BS equals to 5, therefore the missing side QS must be also equal to 5. Okay, so here QS equals to 5. Then we join points O and S together by a straight line. Point O is the center of the circle. Point S is the point of the circle itself. Therefore, OS is the radius of the circle that is equal to R. We have the radius OS that is 1 to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Then I copied quadrangle SOQB in the new page, and we analyze triangle quadrangle SOQB. This is quadrangle QBOS that are copied from the original drawing. Those two angles are equal to 90 degrees, this angle equals to 60 degrees, and this is the missing angle. What is the value of the missing angle? The size of the missing angle will be equal to 360 degrees. This is the sum of the angles in any quadrangle minus the sum of the 3 other angles. So here, this angle QOS will be equal to 360 degrees minus 90 degrees minus 90 degrees minus 60 degrees. So it is 360 degrees minus 240 degrees, that is 120 degrees. So the missing angle is equal, this angle equals to 120 degrees. Here this angle equals to 120 degrees. Then I presented to you the law of cosines, and we implemented the law of cosines in the green triangle, triangle SOQ. What is the law of cosines? The law of cosines is true in any triangle. So we have here triangle ABC that could be any triangle. Side AB equals to A units, side AC equals to B units, and side BC equals to C units, and the angle between side AB and side AC is theta. Then according to the law of cosines, we get that C square equals to A square plus B square minus 2 times A times B times cosine theta. We implemented the law of cosines in this triangle, triangle QOS. According to the law of cosines, in this triangle, triangle QOS, 5 square equals to R square plus R square minus 2 times R times cosine 120 degrees. So 5 square is 25, R square plus R square is 2R square, and minus 2R times R is minus 2R square. Cosine 120 degrees is minus 1/2. So we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. And we have minus times minus is plus. So in conclusion, we found out that 25 equals to 2R squared plus R squared, that is 3R squared. We divided this equation by 3, and we found out that R squared equals to 25 over 3. And the area of any circle is pi R squared. The area of our circle is pi R squared, but we have already found out that R squared equals to 25 over 3, so we can substitute R squared in this equation by 25 over 3. We did it, and we got that the area of our circle is equal to pi times R squared, and R squared is 25 over 3. So the area of our circle, in conclusion, equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 50.265 square units. Okay, so we finished with the first question, then I presented to you the second question, and we solved the second question in 3 different methods. Okay. So in the drawing, we have a quarter circle. Inside the quarter circle, we have a small circle. Line segment CD equals to 8 units. Angle ACD equals to 90 degrees. And our mission is to find out the value of the green area. So we started with the first method. In the first method, we define the center of this circle as point J. Here, J is the center of the circle, E is the point of the circle itself, therefore J is the radius of the circle, that is equal to R. Point J is the center of the circle. Point F is the point of the circle itself, therefore JF is also the radius of this small circle, that is equal to R. We have the radius JE that is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Then we have the radius JF that is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. This is a quarter circle, therefore point O is the center of the quarter circle. This angle equals to 90 degrees, and this AO must be the radius of the quarter circle that is equal to capital R according to our definition. Okay, then from point J, that is the center of the small circle, we draw perpendicular on CO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point J and CO as T. So inside quadrilateral CO TJ, inside this quadrilateral, we have 1, 2, 3 right angles, therefore the fourth angle must be also, here this fourth angle must be also equal to 90 degrees. Inside quadrilateral TJOF, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So this angle EJF, equals to 90 degrees plus 90 degrees, it is 180 degrees. So angle EJF equals to 180 degrees, therefore angle EJF is a straight line. If angle EJF is a straight line, then line segment EJF is a straight line, and if line segment EJF is a straight line, then line segment EF is also a straight line. So if line segment EF is a straight line, then quadrilateral CEOF is a rectangle. Why? Because quadrilateral CEOF has 4 right angles, therefore it is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to CF, CO equals to EF. But we know that EF equals to R plus R, that is to R. So EF equals to 2R, and from this equation CO equals to EF equals to 2R, we will derive that CO is also equals to 2R. Here CO equals to 2R. So here this angle is actually equals to 90 degrees according to rule number 3. Why? Because AO is the radius of the quarter circle, therefore AO is a radius, it is a straight line. So if you focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees. So this angle equals to 90 degrees, plus the missing angle, in total they must be equal to 180 degrees according to rule number 3. So the missing angle must be also equal to 90 degrees. That is the reason that this angle equals to 90 degrees. Okay, so here we implemented the Pythagoras theorem. We join points O and D together by straight line. Point O is the center of the quarter circle, point D is the point of the quarter circle itself, therefore OD is the radius of the quarter circle, that is equal to capital R. Then we implemented the Pythagoras theorem on the right hand triangle DCO. And the right angle DCO, according to the Pythagoras theorem, DO square equals to DC square plus CO square. Okay, again, DO square equals to CO square plus CD square. So DO is capital R, therefore DO square is capital R square, and CO equals to 2R, therefore CO square is 2R squared, that is 4R square, plus CD square. CD is 8, so CD square is 8 squared, that is 64. Here we subtract the 4R square from this equation and found out that according to equation number 1, capital R square minus 4R square equals to 64. What is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle is equal to pi times capital R squared, that is the area of the circle, over 4, minus the area of the small circle, that is pi R squared. Here we took pi over 4 as a common factor out of those two expressions. What is left from pi times R squared over 4, after we took from it pi over 4 as a common factor, what is left is a capital R squared. What is left from minus pi R squared after we took from it pi over 4 as a common factor? What is left is actually minus 4 R squared, because minus 4 R squared times pi over 4 is minus pi R squared. but this expression capital R square minus 4R square equals to 64. Therefore, we can substitute capital R square minus 4R square by 64. We did it and we got that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So in conclusion, we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the first method, and I presented to you the second method. In the second method, we already found out in the first method that CO equals to 2R. Those are the radii of the small circle. This angle equals to 90 degrees according to the first method. AO is the radius of the quarter circle. We already found out that what is the value of AC? Value of AC is AO times CO. AC equals to AO times CO. AO is capital R and CO is 2R. So in conclusion, we found out that AC equals to capital R minus 2R. Then we completed the quarter circle to a circle. We extended the radius AO by straight line until it intersects with the circle at point T. Point O is the center of the circle. Point T is the point of the big circle itself. Therefore, OT is the radius of the big circle that is equal to capital R. Then we extended the straight line DC by straight line until it intersects with the circle at point M. When we extend the straight line by straight line, the result is a straight line, therefore DM is a straight line. So if we focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have here? This angle equals to 90 degrees plus the missing angle. In total, it must be equal to 180 degrees. So the missing angle must be equal to 90 degrees in order to complete the sum of the angles in the lower side of DM at point C to 180 degrees. This angle must be equal to 90 degrees. So we have here two right angles, triangle CDO and triangle OCM. We proved that those two right triangles can go into each other. Why those two right triangles can go into each other? First of all, CO is a common side that belongs to both triangles, so CO equals to itself. In the next step, we have DO equals to OM. They are both the radii of the big circle, therefore they are equal to each other. So by proving that the hypotenuse and one perpendicular of those two right triangles can go in, we prove that those two right triangles can go into each other. Here we prove that CO is equal to CO and OM equals to OD equals to capital R. And it is enough to prove that the hypotenuse and one perpendicular of two right triangles can go in order to prove that the two right triangles can go into each other. Why? Because if, for example, we have two right triangles here, triangle ABC and triangle DEF, and they have the hypotenuse AC is equal to the hypotenuse DF, and the side AB is equal to side DE, they are both equal to 4 units, therefore they are equal to each other. So if we have the hypotenuse and one perpendicular that can go in, the third side must be also congruent. Why? Because according to the Pythagoras theorem, here the third side equals to the square root of 5 square minus 4 square. That is 25 minus 16 is 9, and the square root of 9 is 3. Here also, EF must be equal to the square root of 5 square minus 4 square. That is 3. So here we can conclude that if we have two right triangles with perpendicular and the hypotenuse that can go in, then the third side also can go in. Therefore, the two right triangles can go into each other according to side rule. Okay, triangle COD can go into triangle COM according to side rule. And from the fact that those two right triangles can go into each other, we derive that CD equals to MC. CD equals to MC, according to the rule that corresponding sides in one triangles are equal to each other. But CD equals to 8, and from this equation 8 equals to CD equals to MC, we will derive that MC is also equals to 8. MC equals to 8. We have already found out that OT equals to R, AC equals to OT equals to capital R, and AC equals to capital R minus 2R. Then implemented rule number 11 in our formula. According to rule number 11, if we have chord AB that intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OD equals AO times OB equals to CO times OD. Here we have chord AT that intersects with chord MD at point C. Therefore, according to rule number 11, we get that MC times CD equals to AC times CT. Repeat again, we have chord AD that intersects with chord MD at point C. Therefore, according to rule number 11, we get that MC times CD equals to AC times CT. MC is 8, CD is 8, so 8 times 8 is 64. AC equals to capital R minus 2R, and CT equals to capital R plus 2R. So in conclusion, we found out that 64 equals to capital R minus 2R times capital R plus 2R. And according to the algebraic identity that A plus B times A minus B equals to A squared minus B squared, in our specific expression, A equals to capital R and B equals to 2R. And according to the algebraic identity, this expression must be equal to A squared minus B squared. That is to say, this expression equals to A squared. A is capital R, therefore A squared is capital R squared. Minus B squared. B is 2R, so minus B squared is minus 2R squared. So in conclusion, we found out that 64 equals to capital R squared minus 2R squared. That is to say, 64 equals to capital R squared minus 2R squared is minus 4R squared. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. And what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. Here the area of the green shape equals to the area of the quarter circle minus the area of the small circle. That is to say, the area of the quarter circle is pi times capital R over 4 minus the area of the small circle, that is pi R squared. We took pi over 4 as a common factor, so inside the brackets we left only with capital R squared minus 4R squared, but we have already found out that capital R squared minus 4R squared equals to 64. Therefore, we can substitute here capital R squared minus 4R squared by 64. We did it, and we got that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the second method. Then I presented to you the third method. In the third method, we have already found out, according to method 1, that CO equals to 2R. Those are the radii of the small circle. AO is the radius of the quarter circle, that is capital R. We have already found out that AC equals to capital R minus 2R. Then we completed the quarter circle to a semicircle. Point O is the center of the semicircle. Point T is the point of the circle itself, therefore on the semicircle itself, therefore OT is the radius of the semicircle, that is equal to capital R. So here we extended the radius AO by a straight line. When you extend a straight line by a straight line, the result is a straight line. So AT is a straight line that passes through the center of the semicircle, and it is equal to capital R plus 2R. So we have a straight line that is equal to 2R and passes through the center of the semicircle, therefore AT must be the diameter of the semicircle. AT is equal to times capital R and passes through the center of the semicircle, it is the diameter of the semicircle. Then we join points C and D together by straight line, we join points D and A together by straight line. This way we created the peripheral angle ADT. The peripheral angle ADT rests on the diameter of the circle, that is AT. And we have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of the circle must be equal to 90 degrees. We have peripheral angle A and B that rests on AB, that is the diameter of the circle, therefore according to this rule number 5, peripheral angle A and B equals to 90 degrees. We can implement rule number 5 in our drawing, because in our drawing we have peripheral angle ADT that rests on AT, that is the diameter of the semicircle, therefore peripheral angle ADT equals to 90 degrees according to rule number 5. So this angle equals to 90 degrees. So if we focus on the right triangle ADT, this angle equals to 90 degrees. Okay, and we define this angle as alpha, this angle is as beta. So in the right triangle ADT, this angle equals to 90 degrees. So the rest, the sum of the rest two other angles must be equal to 90 degrees, according to the rule that 90 degrees plus 90 degrees is 180 degrees, that is the sum of the angles in any triangle. That is to say, alpha plus beta must be equal to 90 degrees. Here we subtracted beta from this equation and found that alpha equals to 90 degrees minus beta. Then we subtracted alpha from this equation and found out that beta equals to 90 degrees minus alpha. Then we focused on the right triangle ACD. On the right triangle ACD, this angle equals to beta. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus beta. But we only found out that 90 degrees minus beta equals to alpha, so we can substitute 90 degrees minus beta here by alpha. Then in the right triangle CDT, this angle equals to 90 degrees. This angle equals to alpha, so this angle must be equal to 90 degrees minus alpha. But we have only found out that 90 degrees minus alpha equals to beta, so we substitute 90 degrees minus alpha here by beta. Then we proved that the right triangle ACD is similar to the right triangle DCT. Why those two right triangles are similar to each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. In addition, those two angles, they are both equal to beta, therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So we actually found out that those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that AC over CD equals to CD over CT. Again, we derive that AC over CD equals to CD over CT. AC equals to capital R minus 2R. CD equals to 8. And CT equals to 2R plus capital R. So in conclusion, we found out that capital R minus R over 8 equals to 8 over capital R plus 2R. We cross multiplied this equation number 1, and we found out that 8 times 8 is 64. So 64 equals to capital R plus 2R times capital R minus 2R. We have already found out that capital R plus 2R times capital R minus 2R equals to capital R square minus 4R square. So in conclusion, we found out that according to equation number 1, 64 equals to capital R square minus 4R square. And what is the area of the green shape? The area of the green shape, it is equal to the area of the quarter circle minus the area of the small circle. Again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. We've already found out that the area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle that is equal to pi r square. We took pi over 4 as a common factor of those two expressions. So inside the brackets we left only with capital R square minus 4r square. But we have already found out that capital R square minus 4r square equals to 64. Therefore we can substitute capital R square minus 4r square by 64. We did it and we got that the area of the ring shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So we actually found out that the area of the green shape according to the fourth method equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. So in all three methods we found out that the area of this green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. Okay, thank you very much.